Hi, everyone. This is Tejas here. It's a pleasure and an honor to be here at the HTAP Summit. I'll just give a brief introduction about what I do at Netflix. Why is privacy-preserving compute important? And what are some of the techniques for privacy-preserving compute? Mostly covering, barely just scratching the surface around federated machine learning, differential privacy, secure multi-party computation, and homomorphic encryption. These are terms that you will hear a lot especially in today's world where we have a lot of machine learning AI applications being built, with security and privacy being one of the foremost pillars of enterprise applications. So just to give a brief introduction about myself, I work at Netflix as a senior software engineer. I work on the cloud infrastructure for Netflix studios. Specifically around storage and transfer solutions that allow Netflix to make movies. I'm also a Tech 40 under 40, a TEDx speaker. I speak on cloud and blockchain. I am an adjunct professor for a university in Arizona, and I have experience working at companies like Box, Apple, Samsung, Cadence, and Datrium. So before I get into privacy, I want to just mention that we are at a cusp of an interesting time with generative AI and blockchain. We now are in a world where if you look at data around us, we have been able to move from the pre-internet era where both processing, storing, as well as sending of the data was all in centralized. Then came the internet era, where we have the transfer, which is the sending of the data, that part solved by the internet. However, processing and storage of data was still centralized. Blockchain, on the other hand, is very revolutionary in some ways, because what it does is it says that even storing of the data can be decentralized. And because storage of data is decentralized, interestingly, even processing of the data can become decentralized. This is why I started diving into blockchain initially. However, when you think about blockchain, it's not secure. For a lot of blockchains are not secure. And the reason is that the data is not private. Anyone can look at your blockchain address and can look at all the transactions that have happened before. This is what led me into privacy preserving compute. I wanted to see if there were any applications of, preserving the privacy while still managing compute on top of it. We all use WhatsApp a lot. One of the things that you see in WhatsApp is that it's end-to-end encrypted. It was very strange when I was, a friend of mine was having a conversation on WhatsApp, and it was supposed to be end-to-end encrypted, but later on they started seeing some messages on their LinkedIn and some advertisements, which was directly related to their WhatsApp conversation. That made me think, is it really encrypted? And if it is encrypted, how is someone able to read that message? This is what some of the techniques that I will explain can do. They can actually apply compute on top of encrypted data. Also, we live in a world where there are a lot of breaches of data. As you can see here in this diagram, there is around 52% breaches that were discovered by auditing and assessment, 36% that were just compliant, as well as you can see that the breaches, at least 46% are because of a lost or a stolen compute device. But there are a lot of malicious insiders as well that cause breach. The data in general is not secure, and that leads to a lot of breaches. I would also like to take a moment to explain that we need to understand what is the difference between privacy and security. It is very similar to the difference between authentication and authorization. Authentication is security. Authorization is privacy, because you can tune the amount of control that someone has to view a particular piece of data. We live in a world where we interact with services that keep our data. And when this happens, breaches all the time. Many of you would have heard about breaches in several companies. There was a breach at Uber that happened a while ago, like around a year ago, where their entire infrastructure was compromised. The Slack channels were compromised. When you use a service, you will end up giving your data, and the data can be breached because it is not secure and it is not private. We have also seen around 500 million records containing information of guests that was breached when there was a Marriott data breach. There was an Equifax data breach as well, where 143 million records containing personal information of consumers was leaked. This is one end of the spectrum where you have given your data and the data is not secure. And then what happened? Because we realized that this is happening, we went to the other end of the spectrum where we said, let's not give out any data at all. This is what happens in healthcare today. So let me talk about COVID-19, because it's been one of the most interesting phenomena that has happened in the recent time. If you were to research the impact of COVID-19 on lungs of human beings, this is an actual picture of a patient who had COVID-19. How would you do that? The first step is to download millions of images to train your model. Where do you get these millions of images? You have to buy the data set from hospitals because that data is private. Now, to buy, you need money, and you need to get funded by a VC. You need to create a business plan. So pretty much, you can understand that all of the any research on healthcare data or any research on diseases gets lost in just the data collection process. And this is because we do not want the health data to be compromised. But is there a way you can still maintain the privacy of healthcare data, but get the learnings from them? What will happen then is that, let's say the Stanford Medicine Group has patients that have that you can actually learn from, and you have collected the data. You can train your models on that data and then apply that model to another hospital. That is what privacy preserving computation can allow you to do. Because we are not, because of the fact that the data is private, we are unable to solve the hard problems around us. We cannot detect or predict diseases before they happen. And it really boils down to, is there a way to actually keep the data private but get learnings from the data? That is the entire idea behind, can we answer questions without looking at the data? What does that mean for recommendations? Even know that I am buying something. How will they recommend things to me? I don't, and it doesn't just stop there. You can imagine all the different search capabilities that you use on Netflix for recommendations or on Google for recommendations. So do we really have to compromise on utility for privacy? Privacy preserving computation techniques allow us to get utility, privacy, and security. So on the one hand, in the healthcare example, you have full privacy but no utility. On the other hand, you have full utility but no privacy. We want to be somewhere in the middle, where we get some amount of utility, but we do not give away any privacy. This is what privacy preserving compute enables. So in simple terms, what it does is you own your data, and there are algorithms or compute that run on top of your data without meaningfully understanding your data. And there are several flavors out there. There is, like I said, we will barely scratch the surface here, but there is federated learning, differential privacy, secure multiparty computation, and homomorphic encryption. Let me jump into federated learning. So a lot of you use Apple, and Apple has this thing where you would imagine when you use Siri, the data is being captured in some centralized servers, and then it is trained there and you get recommendations. But that is not what Apple does. What Apple does is, instead of capturing your data and sending it to a centralized server, your data is kept in your device. Instead, Apple ships the machine learning model to the device and trains on the data locally. This is the same case when you type using Google with the autocomplete. The data is stored in your device, and there is no centralized location that is collecting your data. This is called federated learning. As you can imagine, you train your model in a distributed manner on different devices without collecting your data in a centralized repository. And this explains the steps behind federated learning. You have a model and you have data on the edges or the edge nodes. You ship your model to the edge nodes. Your model gets trained by the local data, and only the parameters are updated in the centralized model. So in some ways, you are just you are not ever reading the data out of a device. There are several advantages on federated learning. Only the model gets exchanged between devices and central repository. You are inherently more compliant. When you think about GDPR and other compliance requirements that do not allow you to fetch the data and take the data out to other continents, federated learning gives you an opportunity to just instead get your compute to these devices. However, there are some to it as well. Not all devices are created equal. Some devices may not even have the resources to run those machine learning models and compute. And also there are leaky abstractions here, because even though you are sending back just the parameters, some agent can sniff these parameters and can infer from the model, infer the characteristics of the model. Here is an example how federated learning could be actually used in hospitals. You can have healthcare data that is preserved in these hospitals, and your models can be shipped to these hospitals while also being updated. The updated model can then be applied to a different hospital and get update and work on different healthcare data. And here is actually a paper that talks about how there are privacy leakages from federated learning. This is the reason why you will not really hear a lot about federated learning. It's great because it at least gets us started on this journey, but it is not perfect. Let us now move on to the second part, which is differential privacy. Sometimes AI models can memorize details about the data that they are trained on and can leak these details later on. Differential privacy is a framework that measures this leakage and reduces the possibility of it happening. Before I get into the details, there was no framework to measure how much privacy you are compromising when you share your data. And the claim of differential privacy is that you will not be affected adversely or otherwise by allowing your data to be used in a study, no matter what the study data sets or information sources are available. Now, this is a very long statement, so let me just break it down. In simple ways, let's say we want to know the average amount each individual has in their pocket in the room right now. And we, let's say, add a random number to this amount, plus or minus $20. So let's say individual one has $30 plus minus 20, 40, 50, or whatever, number. The law of large number says that as the sample size grows, the mean will get closer to the average of the whole population, which effectively means that if everyone adds a small noise or a delta to their number, then the average of that would still be the same or close to the average if you did not add noise. This is because all of these deltas cancel out each other as the sample size grows. That is a very simple way to explain what differential privacy implies. It means adding amount of noise that can actually obfuscate the data, but still gather learnings from the data. The key query in differential privacy is that if we remove a person from the database and the result of a query does not change, then the person's privacy in that database is fully protected. In simple words, this is a great example. Let's say you have a database that has entries and another database that has one entry less. If the average of all the entries in database D and the average of all the entries in database D prime is the same, that means the person whose data was removed, their privacy is protected. It does not matter whether they are added to the database or not. They do not affect the result. But if it is not the same, that means their privacy is compromised. That is in short what differential privacy allows us to do. So what does it promise? It promises that individuals are protected from additional harm, but it does not guarantee that what one believes to be one's secrets will remain secret. It promises to make the data differentially private and not disclose it, but it does not promise that the data will be protected from attackers. And now let us move on to the uses of differential privacy. The two most important use cases that I have seen is Google Chrome using differential privacy for frequently visited pages, and iOS using it to discover words and emojis to improve the language models that are used in typing assistance. Microsoft also uses differential privacy to get telemetry data from devices that run their operating system. It was also used by the US Census Bureau in 2020 census. There were researchers that looked into Apple's claim of using differential privacy and found that Apple, although it uses differential privacy, was not really, efficiently leveraging the noise factor that is there in differential privacy that I explained. You can only that variable is called the privacy loss parameter, or epsilon, which determines how much a data collector is willing to sacrifice for the sake of protecting its user's secret. Someone broke into Apple's code and back calculated that this epsilon value is very high, which means that although Apple claimed to be working on technologies that were differentially private, they actually leaked a lot of privacy. So this, in short, explains what differential privacy implies. Now, I would like to move on to the third part, which is the secure multi-party computation. So federated learning, like I said, is not enough to develop privacy-preserving machine learning applications. And however, there is a technique called secure multi-party computation, which parties to perform some computation and receive the result without exposing any of the parties' sensitive inputs. Let's say we have an example here. We have three people, Ali, Brian, and Caroline, and we have, let's say we want to calculate the average salary of all these folks. So we take Ali's salary and we divide it in random order. Here we've divided it into 50, 30, and 20. Similarly, we take Brian's salary and we divide it into 3 parts, and we give each part to each person. So in some ways, everyone is getting a part of everyone's salary, but they don't know the sum of the salary. What secure multi-party computation does is, if we have to compute the average of everyone's salary, we will then just sum all of their salaries together, all of the parts together, and compute the average from each of them. So this means that no person knows the other person's salary, and yet we are able to converge to the result, which is the average. This is another example that you can see where you have a data and you have to shred that data into multiple parts. Each part is provided to a particular node. The nodes operate on only these parts. They communicate amongst each other to compute, to share the results, but they do not know the complete part of any other node. And finally, these results are reconstructed, just like we did with the average case, and we get a result. This is called secure multi-party computation, because all the parties have to communicate, and the data is secure because not all of them know about each other's data. So the blueprint for a multi-party computation is that you securely encode the data. You use some form of a sharing algorithm that does the secret sharing. You compute and you reconstruct the encoded results back. So let us talk about splitting data. So right now, I just split the data in random orders. However, there is some logic into this. There is a technique of splitting the data. And before I get into that, let me just explain basic math that you may have learned in your high school. I'll just give a refresher here. When you have a single point in a plane, there are infinite number of lines that can pass through a point. When you have 2 points, you can have one straight line that passes through 2 points, but you can have an infinite number of polynomials that pass through it. As you add more points, you can have a degree n plus 1 polynomial or degree n polynomial clearly defined by n plus 1 points. That is what we use to generate these shares. Let us say that we have a secret. A secret is nothing but some number that you want to somehow split across All you have to do is make a polynomial pass through that secret, and then take random points in the polynomial and spread it across different nodes. Each node by itself will have no idea about the secret, just because there are infinite polynomials that can pass through the information we have given that node. However, when all of the secrets or all of the nodes can collaborate, we can know that single polynomial that passes through those shares, and we can get the secret back. That is the idea behind splitting this data into secrets. So Shamir's secret sharing is a technique that was invented by Adi Shamir. This is the same guy who's, when you look at the RSA algorithm, the S in that RSA is the Shamir guy. So the information is broken into many shares, but only a fraction will be needed to reconstruct the shares. Also, this is called ITS secure, which is information theoretic secure. What it effectively, in short, means that even after we get quantum computing, we will not be able to break this. And it relies on polynomial interpolation, which is it encodes the secret into a polynomial, splits the data into pieces, and distributes them. So let us now talk about some of the advantages of secure multi-party computation. It can eliminate the trade-off between data privacy and data utility, since private and encrypted data doesn't need to be shared with third party or the model owners. It only reveals the final result compared to federated learning. A machine learning, like in this case, it provides a higher security level. It is less resource intensive as well compared to other techniques. However, there are disadvantages. There is a lot of communication overhead because every node needs to talk to many nodes here. And it is vulnerable to attacks from colluding parties because many of the nodes can actually just say that they have the wrong secret, and then it requires at least some number of nodes. Some number of nodes need to be honest for secure multi-party computation to work. And finally, I will talk about homomorphic encryption. Homomorphic encryption is sort of the holy grail. This is something that we all want to achieve and we all want to get to, but it is very difficult to get to it. It makes your data unreadable and you can still do math on it. By the name itself, you can understand it is a technique of encryption. And for folks may already know, when you encrypt a data, you cannot do any computation on it without decrypting the data. Homomorphic encryption is a technique of encrypting the data in such a way that you can actually perform operations on it. And the idea that when you perform the operations on the encrypted data and then decrypt the result, it would be similar to you performing the operations without any encryption. There are several types of homomorphic encryption. There is the partial homomorphic encryption, where you have select functions that run unlimited number of times. There is a somewhat homomorphic encryption, where you have limited operations up to a certain complexity performed a set number of times. And there is a fully homomorphic encryption, where arbitrary operations can be performed any number of times. So when you are working on homomorphic encryption, there are some relationships that hold true. This is a very simple way to put it. Let's say you have two numbers. You encrypt number A and encrypt the number B. The idea is that if you implement the addition operation appropriately, then the result of the summation of encrypted A and encrypted B is equal to if you had encrypted A plus B together. And similarly, multiplication operation. So what this means is you have to override the addition and the multiplication operations to actually allow homomorphic encryption to take place. And there are several uses as well. It is used in private ML, where a company called CryptoNets applies homomorphic encryption on neural networks. What is tricky in homomorphic encryption is every time we perform a homomorphic operation, we add additional noise to the ciphertext. But at some point, if this noise gets too big, you will not be able to successfully decrypt the ciphertext. You can imagine that for additions, your noise is additive in nature, but for multiplications, it's a problem. That is the entire challenge behind implementing homomorphic encryption. And we don't see a lot of use cases because it is impractically slow. IBM released a HElib C++ library in 2016. And according to an engineer, it ran trillion times slower than plain text. You can totally believe an engineer to use this term. Now it is down to 75 times slower, which is still better. Microsoft also released a simple encrypted arithmetic library. That's Microsoft Seal, which is a library where you can use homomorphic encryption. And this is just the idea behind homomorphic encryption, where you want to encrypt the data in such a way that you can run operations on top of it. An example of where homomorphic encryption could be very useful is cloud computing. Let's say that you are uploading your files to AWS. You encrypt your file in AWS before you send to AWS, and AWS is still able to run operations on top of your file or give you recommendations. That is where homomorphic encryption becomes very powerful, because at no point does anyone need to decrypt your data. So it inherently becomes private and secure. Finally, coming to what is next, what does the future hold? There are several techniques that I've discussed today that rely on very strong computational resources. So we are working on ways in which compute can be decentralized. And so you can then leverage this decentralized compute to build these different types of privacy and security primitives. Fully homomorphic encryption is very aspirational. It requires significant research and a better user experience. All of these libraries that I spoke about, they are all very difficult to use. They do not have any standardization. And so the development is very restricted to researchers. There is no clear interface and there is no benchmarking available. And also these libraries are not interoperable. For SMPC, as we discussed, it requires a lot of message exchange. Are there ways in which we can explore and remove these message exchanges? This is what a company called Nillion is doing. You should check that out. What they claim is you can do secure multi-party computation without actually all the parties talking to each other. Now that has a lot of hope if we want to develop secure operations. That makes secure multi-party computation commercially viable. Ideally, you would want a mix of secure multi-party computation with fully homomorphic encryption, and you would want differential privacy to provide a framework to quantify the risks and how much privacy is being leaked. That's my time. I believe we are at time right now. So thank you so much for joining me. Please feel free to reach out to me. This is my QR code. You can connect with me on LinkedIn. And you can also ask me any questions later on LinkedIn. Thank you.